Multivariable Calculus, Section 13.5, Mass and Centroids. From Wikipedia, in mathematics and physics, the centroid, or center of mass, of a two-dimensional region of a uniform density is the point at which the region could be perfectly balanced on the tip of a pencil. That's in layman's terms. Something like that. In physics, the center of mass of a distribution of mass in space is the unique point where the weighted relative position of the distributed mass sums to zero. The distribution of mass is balanced around the center of mass, and the average of the weighted position coordinates of the distributed mass defines its coordinates. Calculations in mechanics are often simplified when formulated with respect to the center of mass. In the case of a single rigid body, the center of mass is fixed in relation to the body, and if the body has uniform density, it will be located at the centroid. The center of mass may be located outside the physical body, as is sometimes the case for hollow or open-shaped objects, such as a horseshoe. In the case of a distribution of separate bodies, such as the planets of the solar system, the center of mass may not correspond to the position of any individual member of the system. Okay, now there's a little trouble here with the word centroid and center of mass, because many of the sources I looked at said that the centroid was the center point if the density was uniform, and that would be different from the center of mass if the density was not uniform, because if an object was very dense, say at the right end, then the center of mass would move towards the right away from the centroid. However, your book seems to indicate that they use centroid as equivalent to center of mass. And so when they ask you to find the centroid and the density is not uniform, you're actually finding the center of mass. And there were some references that I found that also said the centroid and the center of mass were the same, regardless of density being uniform or not. So we're going to go with the book's definition, even though I really like the other one better. The center of mass plays an important role in astronomy and astrophysics, where it is commonly referred to as the barycenter. The barycenter is the point between two objects where they balance each other. It is the center of mass where two or more celestial bodies orbit each other. When a moon orbits a planet or a planet orbits a star, both bodies are actually orbiting around a point that lies away from the center of the primary, larger body. For example, the moon does not orbit the exact center of the Earth, but a point on the line between the center of the Earth and the moon, approximately 1,710 kilometers below the surface of the Earth, where their respective masses balance. Here's a picture of that, exaggerated quite a bit. The red plus sign is the supposed center of mass. Okay, so enough of this fun. Other ideas related to the centroid. Average or mean of n values. Well, we add up all the n values and divide by the number of values. Average or mean value of a function on a closed interval. So now we have infinitely many values that we want to average. And the average is defined as f of c equaling the area under the curve from a to b divided by the length of the interval. That's the average height of the region. So a centroid is like the average spot in a solid. Mathematical definitions from your text. A lamina is a thin plate of uniform or variable density which can be modeled by a plane region. Density. I use delta of x comma y. Mass. Mass is defined as the double integral over the region of the density with respect to the area. And the centroid, or center of mass, which is the same thing in your text, I think, is x bar y bar, where we compute x bar by taking the density times the individual x points and then dividing by the total mass. And y bar, we take the y values times the density over the total area and divide by the total mass. And so that gives you the spot in the center, in layman's terms, of the object, called the centroid, or center of mass. In all the following examples, we are to compute the mass and then find the centroid, i.e. center of mass. So that's what we will be doing. Number 2, the density is 1. The region is bounded by 4 lines. So here's a picture of the lines, and the region bounded by those 4 lines is there. And if the density is uniformly 1, then the centroid is pretty obviously in the center of that square, but we're going to use our formula to prove that. So our density is 1, and we're going to integrate from 1 to 3 for x and 2 to 4 for y. Antiderivative of 1 is x, and evaluated at 3 and 1, that's just 2. And then the antiderivative of 2 with respect to y is just 2y, and evaluated from 2 to 4, we get 4. Duh, the area is 4 and the density is 1, so the mass is 4. Then for x bar, we have 1 over m, the integral of x times the density. And so 1 over 4 for 1 over m. And then the antiderivative of x is 1/2 x squared, which I evaluated. I put the half on the outside with the 1/4. And we've got 3 squared minus 1 squared, which is 8. And then the antiderivative of 8 is 8y, which is then evaluated from 2 to 4. And we end up with 2 for x bar. Likewise, y bar is 1 over m times the integral of y times density. And so again, it's 1 over 4, and the antiderivative of y is, with respect to x, is yx, and so 3y minus 1y is 2y, and then the antiderivative of 2y is y squared. So we have 4 squared minus 2 squared over 4, and we get 3. And so the centroid is at 2, 3, which is what we knew in the first place. Number 8, the density is still 1. The region is bounded by a curve and a line. So here's what it looks like. There's the curve and there's the line, and the region bounded by those is shown in green. So again, we're going to compute the mass first. And you'll notice that this region is vertically simple. So we're going to have to integrate with respect to y first. And y is going to move from x squared up to 9, and then x is going to move from -3 to 3 all the way across the region. Antiderivative of 1 with respect to y is y, so we get 9 minus x squared for that. And then integrate with respect to x and evaluate from -3 to 3, and we get 36. So the mass is 36 of this lamina. X bar is obviously 0, right? Because the density is uniform, so it's going to be somewhere along that center line. Duh. And then y bar is 1 over m integral of y times the density, which is just y. Take the antiderivative of y, and it's half y squared. I put the 1/2 on the outside. 9 squared minus x squared squared. And then integrate that with respect to x. So we get 81x minus 1/5 x to the 5th. And evaluate from -3 to 3, and we get 5.4. So our centroid is at 0, 5.4, right about there. Center of mass. In this case, all our references would be in agreement. This is the centroid and the center of mass because the mass is of uniform density. Number 14, the density is x squared, so that's not uniform. And the region is bounded by a vertical line and a curve. So there's our curve, and the vertical line is the y-axis, so there's our region. Here's our formula for mass. And this time it's horizontally simple, so we're going to start by integrating with respect to x first. And so we have the density, x squared this time instead of just 1. And so the antiderivative of that with respect to x would be 1/3 x cubed. And then we substitute 9 minus y squared in for x. And when we put the 0 in, we just get 0. So now I wimped out, got the calculator out so I didn't have to multiply all that out. And I got this wacky number for the mass. Now, pretty obviously, y bar is going to be 0 because the top and bottom are going to vary exactly the same way with respect to x squared because the x values are all the same. So even though the density is not uniform, y bar is still pretty obviously 0. Now, if you don't trust that, you can always go ahead and integrate 1 over m times the integral of y times the density. Okay? So now we're going to compute x bar, 1 over m times the integral of x times the density. So there's the reciprocal of mass. And then x times the density is x cubed. Antiderivative of x cubed is 1/4 x to the 4th. So I moved the 1/4 on the outside and substituted 9 minus y squared. And the 0 just gives us 0. And then I typed that into my calculator and got 6. And so our centroid, or center of mass, is going to be at 6, 0, right about there. Number 20, the density is absolute value of xy. The region is bounded by the x-axis, the curve y equal e to the negative x squared, and 2 vertical lines. So there's a picture of the curve and the lines, and the x-axis is part of the boundaries, so there's our region. And pretty obviously, x bar is going to be 0 again because the absolute value of xy is going to be the same on either side of the x-axis. And so we're going to end up there in the middle. Here's our formula for mass, and the region is vertically simple, so we will start off by integrating with respect to y. So on the outer integral sign, we have our x limits from -1 to 1, and on the inner one we have our y limits. And notice that this is going to be symmetric on either side of the y-axis. So instead of worrying about the absolute value and the -1, I'm going to switch that off and make it twice the integral from 0 to 1 for x. And that way I can drop the absolute value because everything's positive. So now we're taking the antiderivative of xy with respect to y. That's going to be x times 1/2 y squared. Evaluated, the y value evaluated from 0 to e to the negative x squared. And 0 is just going to give us 0. So basically it looks like that. And now we can use integration by substitution. Use substitution. We'll let u equal the exponent, and then du is -4x dx. So here's our new integral. Don't forget to change your limits. And then I skipped the simplification, but there's what you end up with. So that's the mass. So now we're going to compute y bar, which is 1 over m times the integral of y times the density. So there's 1 over m, and then the 2 is there because, again, I'm going to multiply the integral from 0 to 1 by 2 instead of using the negative. And so we have y times xy, which is xy squared. The antiderivative of that with respect to y is x times 1/3 y cubed. And notice that I'm going to use a for the coefficient there in the front, so I don't have to keep retyping that. Okay, and then we have to evaluate that integrand from 0 to e to the negative x squared, and the 0 is just going to give us 0. So we end up with a over 3 x times e to the negative 3x squared. And we can use u substitution again. This time u is negative 3x squared and du is negative 6x dx. And so we end up with e to the u, and then I took the negative 1/6 out front and changed my limits of integration to 0 and negative 3. And then I didn't show the calculation there, but that's what you end up with, which can be simplified further. You can get a common denominator of e cubed there on the right. You can factor e cubed minus 1 and cancel some things, and it does reduce a little bit. But that's good enough. And that's approximately 0.4884. And so our centroid is right about there at 0, 0.488, or center of mass, rather. All references would agree that that's the center of mass. Number 30. Now we're going to a polar problem. The density is R, and the region is inside one polar graph and outside the other polar graph. So r equal 2 is a circle, and 1 plus 2 cosine theta is shown in red. And so outside the circle but inside the red would be that region right there. And notice that this is radially simple, and so we can go ahead and use the same ideas from the previous section. So now we need to find out where our endpoints are for our limits of integration are for theta. So we're going to set 2 equal to 1 plus 2 cosine theta and solve, and we get our angles to be plus or minus pi over 3. So here's our formula. It's the same formula except we have to interpret it polarly. So we're going from negative pi over 3 to pi over 3 for theta, and we're going from 2 to 1, starting at 2 and going out to 1 plus 2 cosine theta for r, and the density is r, and then dA, you'll recall, in polar form is another r, dr d theta. So we have one r from the density and one r from the dA. So we integrate r squared, and we get 1/3 r cubed, evaluated from 2 to 1 plus cosine theta. And that gives us this integral when I substitute. And I wimped out and used the calculator for that. And there's the mass, approximately. Now notice that theta, the average theta, is going to be in the middle, 0, because as you move out, the r is going to vary the same way above the x-axis as below the x-axis, and therefore y bar is also going to be 0. And again, if you don't trust your intuition or your logic, you can always go ahead and use the formula. But we'll skip that and go on to the formula for x bar. So we want 1 over the mass times the integral of x times the density. And so I'm just going to keep m there. And so x has to be written in polar form. X is r cosine theta. And then we have r for the density. And again, dA becomes r dr d theta. So we're going to integrate our r cubed. And that's times cosine theta. And that's going to be 1/4 r to the 4th, which I substituted for r to the 4th. I substituted the 1 plus 2 cosine theta and the 2, and 2 to the 4th is 16. And again, I used the calculator to figure that out and substituted 7.962122337 for m, and I got this value, 2.23775, for x bar. So there's our centroid slash center of mass, 0, 2.24 approximately. And now I leave you to do your homework, and with a photograph of a dog that proves that sometimes when a student says, "My dog ate my math homework," it's actually true.